Okay, hello everyone, welcome back. So for this video, we'll just do a few more examples of net ionic equations, and then we will call it good. Okay, so first let me just bring up on my side, so I have it as a reference. So when doing these problems, since I'm not working off the lecture notes, please refer to that chart of solubility rules that I gave you. Okay, so let's do one example here. Let's say we have a solution of sodium chloride and silver nitrate. Okay? And they react to produce a white precipitate of some sort. Okay? So let's predict the reactions. So in double displacement reactions, what's happening is your ions are switching partners. So you're going to combine these two molecules here and now these two molecules. They're going to now switch places. So we get sodium nitrate plus silver chloride. Okay, so is this balanced? Sodium, one nitrate, one silver, one chloride. So it's already balanced. So these are both soluble solutions. Remember, chloride salts are soluble usually with sodium, and then silver, all nitrite salts are soluble. So these will both be aqueous solutions. So say we have two aqueous solutions, and we're going to mix them both. Okay, and then sodium. This will be soluble again because all nitrate salts are pretty much soluble. And then silver chloride here, remember there was an exception in the rule that for chloride salts, the silver is an exception. So we're going to put this as our mysterious white precipitate in solution. So pretty much all halogens with silver are not soluble. So silver bromide, silver iodide, also not soluble. Okay, so this is my condensed equation. So my condensed equation here. Okay, now let's write the total ionic equation. So, if it's aqueous, it's going to be soluble. So we're going to put sodium plus chloride minus plus silver plus nitrate minus. So this will also get you familiar on how to write the ions and their charges. So this is also good practice for that because that is a skill we must have. Okay, then on the other side of the equation, sodium plus, because that is soluble, plus nitrate here. And then we leave silver nitrate, silver chloride by itself because it's not soluble, right? So it's going to stay as the solid, the ionic compound. All right, next for the net ionic, first we're going to cancel out all the spectator ions or ions and the same ions that appear on both sides of the equation. So sodium, and then nitrate and nitrate, okay? So now we have our net ionic equation. This tells us the reaction that's happening in solution. Oops. We get silver plus in solution is combining with chloride ion in solution to generate the precipitate silver chloride. Okay, so that's just another example there. So you see here we we write out our condensed equation, look at the solubility rules, see which ones are soluble, write the soluble ones as ions, and then scratch out the spectator ions, and then we arrive at our net ionic equation. Okay, so the only times you can't separate things into ions are when they form a solid and if they're a weak electrolyte. So weak bases or weak acids, they won't dissociate like we did for the acetic acid example. The only ones that will dissociate are strong electrolytes. So any soluble ionic compound like sodium chloride, potassium bromide, etc., sodium nitrate, and then strong acids and strong bases. So HCl, HNO3, H2SO4, potassium hydroxide, etc. All right. So let's do a few more here just for practice. Okay. So I'm going to erase here, and then to keep things, to avoid writing out things again, I'm just going to keep the names of the equations so we don't have to write it out every time, okay? All right. So say now we have a reaction between sodium hydroxide, well, not sodium hydroxide, sorry. Let's say we have sodium carbonate. So sodium carbonate. Remember, carbonate is CO3 2 minus, so we need 2 sodium atoms, plus HCl, and to give us, so we're going to do 2 things here. First, let's find out what states these are in. So HCl, when it's dissolved in solution, it's a strong acid, so this is going to be aqueous, and it's going to be completely soluble. Sodium carbonate, if we look at our solubility rules here, all carbonates are usually insoluble except when they have compounds with sodium plus, potassium, or ammonium ions. So this one would be soluble, and you could think of it as the conjugate base of, well, I shouldn't be saying conjugate base, we probably don't know what that is, but if you think about baking soda, right, that's very soluble in water, and that's just, it just has one H instead of having no H's in carbonate. So bicarbonate's HCO3 minus, carbonate's CO3 2 minus, so it should be soluble in water, at least its sodium salt variant should. Okay, so that's soluble, but what kind of reaction occurs? So we could think of this reaction occurring, right? It's a double displacement. What happens is they change partners again. Wait, I actually did that wrong. So what happens is sodium now will pair with the carbonate, the chloride, sorry. Carbonate will pair up with the hydrogen. So we could think of this forming. So since carbonate is a relatively weak base, and then HCl is a very strong acid, we could think of carbonate being protonated or getting 2 hydrogens to give you carbonic acid. So H2CO3. And we know carbonic acid, it will be aqueous, but it's a weak acid. However, it's somewhat unstable. And then the other byproduct would be sodium chloride. So in this case, we will need to put 2 sodiums here and 2 hydrogens here, and that will balance out the hydrogens, and the chlorine and carbon and oxygen are already balanced in carbonate. Okay. The only problem with this is that this molecule is an intermediate. That means it's not very stable. So this reaction actually it actually decomposes. So if you ever did that common scientific experiment with the volcano, you put vinegar and you put some acetic acid, And eventually you get a very volatile reaction simulating how a volcano erupts. So what does happen here is that you're forming a very very volatile. You're forming a very let's say you're forming a gas, right? You're forming a gas that wants to escape and not stay in solution. So that gas actually turns out to be CO2. So this compound H2CO3 actually turns into the gas CO2 and water. Okay, so the complete reaction would be CO2 gas plus H2O plus sodium chloride. And we know sodium chloride is aqueous, so we will put aqueous right by its name. Okay, so you get those three compounds. So the reaction is actually, we're going to now erase this because it's unstable, and it turns into this. Okay, so we see here that now the carbons are balanced, the hydrogens are balanced, everything is balanced now. So let's write the net total ionic equation first. So we have 2 sodium plus ions plus CO3 2 minus ion. Now since we have a strong acid here, it's going to be 2H plus 2Cl minus aqueous, and then right here we're going to write the products. Sodium chloride is very soluble in the solution, so it'll be 2 plus aqueous plus 2Cl minus aqueous. So carbon dioxide is a molecular compound, so we cannot decompose it. It's a non-electrolyte, it won't form ions. Same with water. So water is the solvent, so we can't say water aqueous because that makes no sense. Aqueous means dissolved in water or in water solution as a solvent, so we put it as a liquid. Okay, that's what L stands for. Now let's find our net ionic equation, cancel out some spectator ions, the sodium and the chlorines, right? So what we're left with is 2H plus carbonate 2 minus. So this would form carbonic acid, but we know carbonic acid is short-lived, and so it will not exist for it won't exist for a long time, so it will rapidly decompose to CO2 gas. I mean, you can't even, it's not even like a second, it just happens instantaneously, so it's not like you can conserve carbonic acid for a while. It's just not stable, so it will turn into CO2 gas. But carbonic acid is what makes the blood acidic. So we can definitely absorb CO2 into our bloodstream, but it makes the blood acidic. So eventually when it travels throughout the body, it'll have to be expelled because of that acidity, but also because of CO2's limited solubility in water, so it doesn't like to stay there. It doesn't like to stay there for long. So that's why water, we tend to not, we don't tend to keep CO2 around because we want to, it's how we breathe, right? We take in oxygen, and then a byprocess of using that oxygen is CO2 that we then expel back into the atmosphere. And then, that CO2 is pretty much the life source, the energy source for photosynthetic organisms like plants and certain bacteria. So it's kind of like this nice cycle. So we kind of have to think about how we don't overproduce CO2 because there's not enough life on Earth to kind of recycle that back into carbon molecules or glucose. Okay. All right. So, and then we have water as well. Okay. So now let's make sure everything's balanced. 2H plus, 2A hydrogens. The charges are both neutral on both sides. The charges of the reactants and products. And then 1 carbon, 3 oxygens. We're good. Okay, so that's an example of a decomposition or a double displacement and what we call molecular formation of a molecular product. So that's usually H2O or CO2. Okay, so that's one of, it's a special kind of example where you form an unstable product and then it decomposes into a molecular compound. So a compound that does not form any ions. So carbonic acid can form H plus and carbonate, but CO2 cannot form ions. So that's an example of forming a molecular compound. And this is an important reaction. You may see it in discussion. Okay, so let's just do one more example and we'll call it good for lecture 6. Okay, so it's important that we do a lot of these examples because if we don't, come exam or quiz time, we may be, kind of stuck on when it comes to this question. So we don't want that to happen. And in higher levels of chemistry, you will need to be able to do this on a routine basis. And if you cannot, you will not fare well in if you ever go to OChem and in Chem 401. Okay. Oops, I shouldn't erase that. Let me go back here. Let's not erase the labels here because we don't rewrite them. All right. Say we have solutions of potassium chloride. Okay. Solutions, so aqueous solution of potassium chloride and ammonium nitrate. Okay. All right. So we go back to our solubility rules. Chloride salts are usually soluble, so potassium chloride would be a soluble compound, and then ammonium nitrates are soluble, and there's no exception, so both of these should be soluble. If we're predicting a reaction, we would think the potassium would now be paired to the nitrate, and the chloride would be paired to the ammonium, and we would get the following: potassium nitrate and ammonium chloride as our products. Okay, now let's see if they're what the total ionic equation should be. So we know potassium chloride is aqueous, so it should be soluble plus chloride. But first, let's double check if it's balanced. We have 1 potassium, 1 nitrate, 1 nitrate, 1 ammonium, 1 chloride. So 1 chlorine atom. So we're balanced. Okay. Now we already determined that these compounds are both soluble. Okay, now potassium nitrate, remember there's no exceptions for nitrate, so that's also soluble. Oh, but also ammonium chloride is also soluble. It's not one of the exceptions, so everything is soluble. So there's no precipitate, right? So let's just write these out here. So in this particular case, we get a situation where every ion on both sides of the equations are spectator ions. So chlorine will cancel out, nitrate, ammonium, potassium. So this is where we get a situation of no reaction. All spectator ions. So every ion is soluble, so they like to hang out with water, so no reaction will occur between any of the ions in solution. So this is no reaction. So we can also have situations like these, no reaction. Okay, so I think that's pretty good for writing net ionic equations. If we need more practice, remember we'll do that in discussion, also in the homework, and then there's more practice problems on Canvas. Okay, so that's it for lecture 6, and that's it for lecture this week, and I'll see you next week. We'll start talking about acid-base chemistry and redox reactions. Okay, see you then.